So bevel gears are different in terms of the axis of the shaft. So if you think about the bevel gears, so bevel gears can transmit power at an angle. So the shafts could be perpendicular to each other, or the shafts could be at an angle that is not 90 degrees. So classic example of bevel gear application is the differential drive. And when we have a differential, in the case of the front wheel drive or the rear wheel drive, and the power needs to be transmitted from the engine, the axle, you have something called as the differential. So many a times, if you have a rear wheel drive, what they call it a pumpkin, you would see a pumpkin in the back. That is where the differential mechanism is located and continuously circulated oil. So bevel gears are used in important applications. There are two types of bevel gears. One is the straight bevel gears, and they are also called as meter gears. So the types of bevel gears, there is something called as meter gears. And the second one is angular bevel gears. So basically, in meter gears, you have same number of teeth, and they are perpendicular to each other. And in the case of angular bevel gears, they are at an angle. And you can have crown bevel gears, you can have internal bevel gears. Some of the important properties and in the nomenclature is, if you think about the bevel gears, they are like part of a cone. So if I were to extend the bevel gear, you will notice that they intersect at this point O. And this point O is called as the cone center. So cone center is where, if you were to project or extend the bevel gear profile, the bevel gears are going to intersect. Now, typically, if you look at the bevel gear design, the bevel gear, I just want to show you the design. They have something called as the front cone and the back cone. So this is the actual bevel gear. So what it means is you can extend the bevel gear, or you can project it ahead, or you can project it behind. So you can have, this is called as the front cone, and this is called as the back cone. Now, again, some important dimensions are the cone distance, and then another important dimension is the cone angle. But most important relationship that I want you to think about is basically, if you think about this distance, it is the hypotenuse of triangles. So there is one triangle here, and then there is another triangle which is over here. And let me show you slightly enlarged view. That would make this discussion more sense. So what we have is we have gears meshing over here, and then we have these gears intersecting at the cone center, and I want you to look at this distance. So this is called as the semicone angle. So I'm going to call this theta 1, and this is also called as the semicone angle theta 2, because this I'm going to call gear 2, and I'm going to call this gear 1. Now, if you notice this portion, so let me show you this portion, this length, I'm going to call this AB. This is the pitch circle diameter of the gear 1. Here is the pitch circle diameter of the gear 2. So this, I'm going to call this as D1. And I'm going to call this D2. So I want you to look at the triangle that I have drawn. This triangle is something like this. This is D1 by 2. This is D2 by 2. This angle is theta 1. This angle is theta 2. So based on the geometry, I can write this equation, D1 by 2 divided by sine theta 1, that gives me AB, which is same as D2 by 2 divided by sine theta 2. So this is an important relationship that I want you to remember. Based on the geometry, this semicone angle needs to be, this condition for the semicone angle needs to be satisfied. And then you are going to have the pitch angle, cone distance, then addendum angle, dedendum angle, face angle, and all their parameters. Because if you think about the bevel gear is not cut in a plane. It's actually a sort of a three-dimensional structure. Similar to spur gear and helical gear, you would have addendum, and the relationships is 1m, dedendum is 1.2m. You can have clearance, which is 0.2m, working depth, which is 2m, and then where m, it goes without saying, m is equal to module. And important thing to note is the velocity ratio, just like what we discussed earlier, is dependent on the number of teeth on the pinion and the number of teeth on gear. So velocity ratio, again, we will use the same equation, and then for the gears, and then we'll work out the reduction ratio and so on. Now, there is something that needs to be discussed in the case of bevel gears. So bevel gear, it is very important to note, has a three-dimensional geometry. Now, here is what we want to do. If you look at the procedure for helical gear design, what we did, we started with a helical gear. We converted a helical gear into an equivalent spur gear, and then we designed, basically assuming the spur gear. The tables and everything was used for the spur gear. In the case of helical gear, approach is exactly the same, or in the case of bevel gear, approach is exactly the same. What we would do is we would take the number of teeth on the bevel gear and convert that into an equivalent spur gear. So once we know the number of teeth on the bevel gear is at 10, we would find out what is the equivalent number of teeth for the spur gear. And that relationship is obtained by means of something called as Treadgold's approximation. So Treadgold approximation is a technique to find equivalent number of spur gear teeth for bevel gears. And just to give you some sort of perspective, I want you to think about the spur gear. If you have an involute profile, you are going to have line rolling on a circle. But if you think about the bevel gear is actually not a circle, but it's a cone. So in other words, it sort of becomes the surface of the sphere. And that approximation, the geometric approximation to construct a spur gear profile from a bevel gear profile is Treadgold's approximation. But at the end of the day, once you perform the Treadgold's approximation, what that means is you are going to get the equivalent number of teeth. So the relationship that we obtained is TE is equal to T divided by cosine theta P. So this is the determination of equivalent number of teeth for helical gear. And once you do this calculation, you have TE, and then you would follow the exact same procedure as spur gears. So let me give you the recipe. So step 1 is the strength calculation. Which is WT sigma O multiplied by CV multiplied by B multiplied by pi multiplied by M multiplied by Y prime, which is the modified Lewis form factor. So far, this equation is exactly similar as the bevel gear, as the helical gear. But since it's a bevel gear, there is one thing that changes, which is L by B by L. And L is nothing but the slant height or the length AB of cone. So L is slant height or the height, the distance AB of the cone, which can also be found out as square root of radius of the first bevel gear plus radius of the second bevel gear square root. So using the Pythagorean theorem, we can find this out. And B is face width. Sigma O is the strength equation, strength of the material. CV is the velocity factor. We would use typically the velocity factors for bevel gears as 3 divided by 3 plus V, or 6 divided by 6 plus V. So this is the regular and these are precision. This factor is sometimes called as the bevel factor. The next part, just some guidelines. So for the bevel gear, typically the value of B is considered to be 6.3 to 9.5 times module. So the face width for the bevel gear is usually between 6.3 to 9.5. The L by B ratio is typically should not exceed 3. I mean, there are special circumstances when you can make an exception, but L by B ratio you should try to get that less than 3. And another important relationship that will be very useful is minimum number of teeth. On the pinion is a small gear, is 48 divided by square root of 1 plus VR, where VR is the velocity ratio or gear ratio. So when we are trying to design a bevel gear, the first thing that we need to find out is what is the velocity ratio. Once we know the velocity ratio, we can find out the minimum number of teeth. And once we know the minimum number of teeth, the same relationship, which is pitch circle diameter, D is equal to number of teeth multiplied by module. This equation can be used, and then we would use the strength calculation equation and find out the module. So when we substitute, all said and done, from step 1, you will obtain module. Now, the second step, just like spur and helical gear, step 2, is determination of dynamic load. And again, for determination using Buckingham equation, we can use the equation that we studied in spur gear design, and that should be able to give us, we can use this exact same equation, and that should be able to give us the dynamic load. And I would just duplicate that equation here for reference. This is the exact same equation from the spur gear. And using the table 28.5 onwards, you can find out the values of C and other values. The next part is determination of the static load. Step 3. Ws is given by the equation sigma E multiplied by B multiplied by pi times M multiplied by the Lewis's form factor multiplied by the Bevel factor. And for design to be safe, Ws has to be greater than Wd. The next step is determination of wear load. And that is given as same equation as the spur gear, Ww, and it's always done for the pinion, dp times b times q times k. The only difference here is you will divide that by the semicolon angle, cosine theta p1. This is the semicolon angle for pinion. So that is what we have to keep in mind. And Q is equal to 2 times TEG divided by TEP plus TEG. So a word of caution, when we find Q here, we use formative number of teeth. In other words, we would use the equivalent number of teeth. Now the next part comes how to design the shaft. So next part is shaft design. And for shaft design, we need to find out the forces on the gear. So just like helical gear design, the bevel gear has a 3-dimensional state of stress. So I will give you the equations for Wt is tangential load, Wn is tangential load divided by cosine of phi, which is the pressure angle, and Wr is equal to Wt multiplied by tan phi. And some of you may ask me, why isn't there the helix angle? And the reason there is no helix angle in this case, because these are straight cut gears. So your helix angle alpha is equal to 0. But if there is a helix angle, then you can use the exact same equation as the helical gear, and you can get the tangential, radial, and in that case, you are going to have axial loads. So let me show you what I mean by that. So if you think about the bevel gear is going to look like this. This is a straight bevel gear. So if you were to look at the bevel gear where the teeth that are cut are at an angle, then you will notice it would be something like this. And this would have alpha is equal to 0 and alpha value would be a non-zero. This is similar to spur gear shaft design. And this is similar to helical gear shaft design. So what it means is you have to find out the moments. So resultant moments. And then you have to find out the equivalent torques. And then use the equation and get the value of diameter. So in terms of shaft design, the process is similar. The only thing what you want to take into account is what type of support the bearing has. If the bearings are cantilevered, means the gear is supported only on one side, or you have bearings on the both sides of the helical gear. In other words, the helical gear is supported in a simply supported shaft. Okay, so what I'm going to do is I am going to work out a problem. Quickly, any questions on the recipe that we talked about? Any questions? If there are no questions, let me work out a problem. So a pair of cast iron bevel gears. The shafts are at right angles. And in this case, the diameter of the pinion is given to us. Diameter of the pinion is 80 millimeters. Diameter of the gear is 100 millimeters. The tooth profile is 14.5 composite. Allowable static stress sigma O 55 Newton per millimeter square. If the pinion transmits, so the power transmission is 2.75 kilowatts at 1100 RPM. We have to find the module. We have to find number of teeth, and then we will check for wear. And we would use surface endurance strength as 630 Newton per millimeter square, and the modulus of elasticity 84 kilonewton per millimeter square. So in this gear design, we are going to start from straight, starting from step 1. We are going to find out the semicolon angle. So step 1, as we know that dP divided by sine theta p is equal to dg divided by sine theta g. We also know, since both these gears, the shafts, are perpendicular, theta p is equal to 90 degrees. So now we have two equations and we have two unknowns, 40 50 divided by sine theta g So we have equation 1 and we have equation 2. From these two equations, actually I made a mistake, this is not sine, this is cosine. So from here, you can find out the value of theta p, you can find out the value of theta g. Now, theta p and theta g, so theta p is 38.6 and theta g is 51.3. Now, since both of these are made up with same material, since gear and pinion are of same material, pinion is weaker, and the design should be based on the pinion. So what we are going to do is we are going to find out the equivalent number of teeth for pinion, and then we are going to find out the values of Lewis form factor for pinion. So equivalent number of teeth for pinion is going to be the diameter of the pinion divided by the module divided by cosine of theta p, which is 80 divided by m. Theta p is 38.6. And that comes out to be about 102 divided by m. Now with that, we should be able to find out value of y. And since it's a 14.5 composite, so we can use the Lewis form factor equation, 0.124 minus 0.684 divided by TEP. So with this, you get 0.124 minus 0.684 divided by 102 multiplied by m. And then that leads us to determination of pitch line velocity, which is pi times dp speed divided by 60. Pi times 0.08 times 1100 by 60. That gives you 4.6 meter per second. Velocity factor is equal to 6 divided by 6 plus Vp as given in the problem. 6 and 0.566. Now in the equation, we are going to need the slant height. L is equal to square root of 50 square radius of the gear, radius of the pinion. That gives me 64 millimeter. And with that information, we are ready to solve the problem. We are going to use the criteria face width should not exceed L by 3. We are going to use face width at least 1/3. So which is 64 divided by 3, which is approximately 22. Next step. So next step is going to be determination of torque. Torque is equal to power times 60 divided by 2 pi n. So power is in watts 2750 times 60 divided by 2 times pi times n is 1100. So that gives me 23.8 Newton meters. Now Wt is equal to torque divided by diameter of pinion by 2. Please note that since the gear and pinion are made of the same material, we are going to use the diameter of pinion. So which is 23.8 10 to the power 3 divided by 80 divided by 2. That gives us 600 Newton. Now with that, we can find out the equation. Wt is equal to sigma O times velocity factor times B times pi times m y prime multiplied by the Bevel factor. So sigma O is given as 55. CV is the velocity factor, 0.566 times B, which is 22 times pi times M times Y is the equation that we determined in terms of M multiplied by 64 minus 22 divided by 64. So, and on the left hand side, you're going to have 600 newtons. You can solve this equation, again, trial and error, and your module would be 5 millimeter. So at this point, gear design is done. We can find out number of teeth on pinion is equal to TP is equal to dP by M. Number of teeth on gear TG dG by M. So you will see 16 and 20. Now next step is checking for wear. And in this case, I just want to take a slightly different approach. You can use the table approach, but alternatively, you can find out the value of K in the equation, which is sigma ES square sine of P, which is the pressure angle, 1.4, 1 divided by EP plus 1 divided by G. Then there's going to be 630 square sine of pressure angle 14.5 divided by 1.4 multiplied by. So as you can see, this will be 2 divided by 84 10 to the power 3 because EP is equal to EG. And that gets us 1.68. The ratio factor Q is 2 TEG divided by TEG plus TEP 2 times 160 by M 160 by M plus 102.4 by M. That gives you 1.22. And the last part is determination of WW, which is dP times B times Q times K divided by cosine of theta P. 80, 22 times 1.22 times 1.68 cosine of 38. That gives us 4640 newtons. And if you want to proceed further, you can find out the dynamic load exactly like spur gear design. You can find out the static load. So, and then make sure that WD is less than WS and WD is less than WW. This is similar to spur gear design. So with this, you should be able to solve the bevel gear design problems. So any questions on bevel gear design? Any questions? So now do you want me to solve a problem, or can we move on to the worm gear design? And you can type in the chat window, or you can unmute yourself and let me know. Any questions, concerns, ideas? If there are no questions, we will take a break of 10 minutes before switching gears, and then we will start worm gear design. So a break for 10 minutes, not 15, and then we will start worm gear design. So in this class, we are going to look at the design of worm gears. Design of worm gears is actually quite simple, because if you think about the worm is nothing but a power screw. So design of worm gears. Worm wheel. So what is worm and worm wheel? So there are two types of worms. And before that, let me show you. Probably you have seen something like this. You have this big gear, and this big gear meshes with a small gear. But important point here is the axis of the wheel. This is called as worm wheel or wheel. So this is called as worm wheel or wheel. This is called as worm. So the worm rotates, and that causes this worm wheel to rotate. And if you look at the axes, those axes are perpendicular to each other, and they are in different planes. So if you look at the axis of the worm wheel that is coming towards you, it's in the plane perpendicular to the paper. The axis of the worm is along the paper. Now, what are the advantages and disadvantages? So first and foremost, I want you to understand in worm wheel, power transmission is unidirectional. Power transmission only in one direction. Which means if you rotate worm, the worm wheel will get rotated. So if worm is rotated, whether it's clockwise or counterclockwise, worm wheel is rotated. But if you rotate worm wheel, worm will not rotate. which means in this condition, it will be locked. So the power transmission is only possible from worm to worm wheel, and that is sometimes desired. So think about a case that a worm wheel type of mechanism is used for lifting heavy loads. And here is a motor. The figure is not proportionate, but please understand the concept. Here is the motor. So what we want to do is we want to rotate the worm and raise or lower the load. So we want to raise or lower the load by rotating motor. Now consider a case that the power fails and motor stops all of a sudden. So because of this worm wheel arrangement, load will not run. Imagine a case that someone is standing over here. You don't want that load to run away and fall on the ground and cause injury. So if you have a worm wheel type of mechanism, it's sort of a fail-safe mechanism. So in the case of power failure, worm wheel will get locked. Now, what are the disadvantages? Worm wheel efficiency is low, which means lot of power get wasted as a heat. So heat generation. So that is something we need to take into account when we design worm wheel. So if you look at worms, there is cylindrical worm, there is a conical worm, and if you look at wheel, there is a straight, hobbed, and concave. So you have straight wheel, you have hobbed wheel, and you have concave wheel. So these are different types of combinations. And just you think about worm. A worm is similar to a power screw. So worm, you can think about it like you have a power screw and the helix runs across the power screw. So some of the design techniques that we will study, they are similar to the power screw design. And just like power screw, for the worm, you have something called as the axial pitch. So this is the pitch in the axial direction, also called as the linear pitch. Then, just like power screw, you have the concept of lead, which is advancement in one turn. And the relationship between the lead and axial pitch, it comes from the same type of equation. If the axial pitch is PA multiplied by N, where N is number of starts. So if it's a single start worm, then the lead is going to be equal to linear pitch. If it's a multi-start worm, it's going to be lead multiplied by 2 or 3, whatever the number of starts are. Just like power screw, you are going to have a helix angle. So helix angle, so sometimes also called as the lead angle, is equal to tan inverse lead of the worm divided by pi times diameter of worm. So if you think about it, this is the lead angle, lambda. This is pi times diameter of worm and lead. And lead angle can vary from 9 degrees all the way to 45 degrees. And there is something called as tooth pressure angle. And if you look at the tooth pressure angle, basically that depends upon the lead angle. So basically there is the lead angle lambda, and that gives a relationship with pressure angle. So if the lead angle is 9 to 16, 16 to 25, 25 to 35, 35 to 45, this is table 31.1. And this is 14.5, this is 20, this is 25, this is 30. Now in automotive applications, you would see worm mill drive for when heavy power reduction is required. The next nomenclature is nothing but the normal pitch. So just like we talked about the pitch in the axial direction, this is the pitch in the normal direction, which is PA multiplied by cosine lambda. The most important thing in worm mill drive is the velocity ratio. And velocity ratio for worm mill drive is given as velocity of the wheel, so N wheel divided by N worm, and that actually it's worm because worm will be rotating faster, wheel, which is diameter of the wheel divided by diameter of the worm. So this is an important relationship, and this gives you a very interesting, I'm not going to derive this, but that gives you TG divided by N, which is number of teeth on wheel divided by number of starts on worm. So this is an important relationship that we should keep in mind. And typical values for velocity ratios. So if you have a velocity ratio of 36, which is quite high, the number of starts are usually 1. If it is 12 to 36, you get number of starts 2. 8 to 12, you get 3 starts. So there is this guideline, but sometimes based on your design constraints, based on your size constraints, based on the power requirements, you on application, you can choose appropriate values. And this table is 31.2. The next part is if you were to design or if you were to look at the worm wheel, you are going to have the diameter, you are going to have the outside diameter, but it is super important to know that whenever we are designing the worm and worm wheel, we always design worm. Worm is always weak. So worm wheel is mostly based on the proportions. So worm wheel is based on worm design. And the reason for that is, if you think about the relative size, worm wheel is quite big to achieve the gear ratio of 36/40 or something like that. So worm is always weak. And when we work out a problem, it would actually make sense, but I'll give you some proportions. So for worm wheel, you could have normal pressure angle. That could be 14.5 or 20 degrees. Then you could have outside diameter. That could be nominal diameter plus usually PC. Then you can have something called as the throat diameter. That would be like 2.5 times circular pitch plus 6.5. Then you can have gear face radius. That is 0.8 PC plus 14. Gear rim, that is 2.2 PC plus 14. So please look at table 31.4, and then we can find out the answer. Now, in the case of worm wheel, many a times we have to check for heat dissipation. And this process is exactly same. We find heat loss is equal to 1 minus efficiency multiplied by power, and we equate that to H times A times delta T, where A is the surface area. This is the coefficient of heat transfer. And delta T is change in temperature. So let me work out, let me give you the design recipe before I work out a problem. So recipe for worm gear design is again step 1. And please note, we are going to design the worm. So actually correction here. So when we are designing, so basically gear or wheel is weaker than worm. So I made a mistake when I was discussing this. Wheel or worm gear is weaker than worm. So we would always design wheel. So please make that correction. And step 1 is, again, we are going to use the beam strength equation. WT is equal to sigma O multiplied by CV multiplied by the face width times pi times M multiplied by Y. And if you think about the wheel design, which is similar to spur gear design. So we will find out the value of Y. We will find the ratio between M and B. And then we will use the velocity factor CV is equal to 6 divided by 6 plus V. And then Lewis's form factor Y, depending upon we have what type of pressure angle we have, we will use 0.124 minus 0.684 divided by T for pressure angle 14.5, and Y is equal to 0.154 minus 0.912 divided by T if the pressure angle is 20 degrees. The next step is determination of dynamic load. Determination of dynamic load. And that is given as WD is equal to WT divided by CV. Now this is an important difference. So if you have a velocity factor CV, the dynamic load is given as tangential load divided by CV. And typically CV is considered to be 6 divided by 6 plus V. So that is the dynamic load. And then we move on to static load. So for static load, is WS is equal to sigma E times B times pi times M times Y, which is the exact same equation as spur gear. But it becomes easier for worm gear because usually if you have a cast iron worm wheel, then it's usually 68 newtons per millimeter square. And if you have a Prosper Bonds worm wheel, then it is 168 Newton per millimeter square. And the last but not least is determination of wear load. Step 4 is wear load. And to find wear load, again, equation is super simple. WW is equal to DG, which is the diameter of the gear, multiplied by B multiplied by K, where DG is the wheel diameter, then B is the width, and K is the load stress factor, and the load stress factor for worm gear, so this value of K can be found out from table 31.5. So if you look at table 31.5, you have worm, then you have wheel, and for particular combination of worm and worm wheel, the stress concentration, the load stress factor is given. So just to give an idea, if you have a steel worm and you have a Prosper bronze wheel, then the load stress factor is 0.415. If you have cast iron worm and Prosper bronze wheel, then it is 1.035. So this is something that we should keep in mind. And the last part is heat dissipation. Is heat dissipation. So Q is equal to 1 minus efficiency multiplied by power. Now there are two ways to find out efficiency. You can actually, for efficiency, you can use the equation, or for efficiency, you can use the graph. And it's totally up to you, whatever approach you want to use. So you can use the equation for efficiency, or you can use the equation or you can use the plot. And once you find out the value of Q, then you can find out the heat dissipation that actually the amount of heat that is generated, and then you can actually find out whether the worm and worm wheel, are they capable of transferring the heat. And the easiest way to do this is by equating the equation H A times delta T. Typical values of delta T are about 40 degrees, and the typical values of area is the surface area of the gear. So basically, which is pi times the diameter of the gear. And H value depends upon whether you have pre-convection, you have force convection, and that will tell you the value of H. And what we need to make sure is Q capacity. So Q capacity is greater than Q generated. So I'm going to call this QG. So Q generated has to be less than the Q capacity. So worm wheel design is very straightforward. So again, please note I made a mistake. You design the wheel. So we always design the wheel. So this is the guy we design. And this is similar to spur gear. And then you can go through the process. You have axial pitch, lead angle. Then for certain velocity ratios, you decide the number of starts. Then these are the proportions. And then if you look at step one is based on the beam strength. Step two is determination of dynamic load. Again, equation is super simple. Step three, determination of static load, and then determination of wear load. And for design to be safe, it goes without saying, WS has to be greater than WD, and WW has to be greater than WD for safe. And this is how the worm wheel design will be done. And I'm going to stop here. And if you have any questions, I would be happy to answer.